Good evening, and we have a good number of participants, 15 in total connected. So it's time to start, and I want to say just a few words to introduce Gianluca Davoli. He's a researcher assistant professor at the University of Bologna, where he obtained his PhD degree in 2021. His research work revolves around multiple aspects of softwarization in communications infrastructures, service orchestration on the cloud continuum, and he's focusing on far and near edge segment. So Gianluca, thank you very much for this, for giving this tutorial.
Thank you for the introduction.
And by the way, I am Guido Maier, a professor at Politecnico di Milano. I just want to also introduce the topic you are going to discuss today. This tutorial is actually structured in two parts, and today you will get the first part, which provides an historical perspective on software and communication networks, touching the several paradigms and the technologies that are enabled, in particular efficiency, reconfigurability that is brought by softwarization. The second part will be presented on Monday, 31st of March, and it will describe and showcase functionalities on the microservices-based SDN controllers, which are designed as a playground framework for research and teaching. So I don't want to take any more time, and Gianluca, please, you can start. Thanks.
Okay. Thank you very much, Guido, for the introduction, and thank you everyone for being connected here. In fact, as Guido already said, this is the first part of a tutorial which is supposed to span across two different sessions. And in fact, I click those words. Okay. And in fact, the overall goal of this tutorial is to well, it's twofold actually. With my part being mostly about history and mostly about how we got to the point in which, to the point in which we are now, in which software has a really relevant role in communication networks. Whereas the second part will be a little bit more innovative, let's say. So I'm not going to present, I want to say that as a disclaimer for everyone. I mean, I'm not going to present results or like new technologies in this case, but I would like to introduce, so my part would like to introduce some food for thought, and maybe it's for some discussion and some, the kind of comparison between different points of view also. So that's mostly my objective. In fact, so the subtitle that I would like to give to my part would be a retrospective on network softwarization towards network orchestration, which is going to be the endpoint, the final goal of this talk today. I'm going to try to stay within around 1 hour overall, so that after that we have a few minutes for questions or for, well, even discussion. I mean, actually, I would really much appreciate any even corrections or anything that we can discuss on, because that's how we learn. All right. So okay, without further ado, well, actually, with some further ado, let me just give a few words more about myself, but only to basically shed light on Restart, which is the overall thread that unites all these talks, and which is also currently enabling me to perform the research. So I really should be, I would really like to specify that, also within Restart, I am involved in activities that are relevant to what Guido said earlier, that are mainly in Project Super on programmable networks, in which I am a work package leader for work package 2, which is concerned with the development of a well, it's called Dynamic Software Edge Mobile Platform. What it means is basically orchestration at the edge. And I'm also involved in Rigoletto, another Start project that again, mainly in a work package that it's concerned with control and automation, because these are really mainly my areas of interest. And yeah, specifying them here also because, as always, I would also like to say, you know, if there's any room, if you see any room for collaboration, I am always happy to you know, take the chance. Okay, so now without further ado, since my part is going to be mainly like historic, let's say, talking about history, I would like to quote from the Genesis and start by talking about start by talking about the origin of the structure of the internet. I would say, to some extent, it's hard to represent the internet, and that's not my point here. My point here is to show how the evolution of technology can go, because there's some kind of a pattern, as we all know, in which it looks like we're going in a direction, then we're going in the opposite direction, and then the first direction again. This is something that one might think, although this is something that it's really not exactly what's happening. But let me give you an example of that. Think about IP networks. So, well, originally IP was thought as an overlay protocol that was supposed to connect domains which were independent, and each domain had its own routing protocol, its own mechanisms, and it was supposed to be independent from the others. So IP was supposed to be the gateway protocol, the one between different domains. This is actually history, because I mean, this is a few decades ago. Well, then, you know, people realized that we might as well use IP routers even within these independent domains. And at the end, you know, at that point, we got a network which was mainly IP based on every level, I would say, with IP domains interconnected by IP routers, really. So at that point, IP became what's like the network protocol, not necessarily the inter-network protocol as it was supposed to be at the beginning. Then we said, well, okay, but maybe these subdomains, so these independent domains, you know, can benefit from some new approach, in this case from software, actually. And here comes software-defined networking, which is something that has been started to be, you know, at the beginning of software-defined networking. It's something that was mainly deployed, again, in independent domains. So we have, again, independent domains, each of them controlled by software, so with a software-defined networking approach, interconnected to the other domains with IP gateways. So really, it's something that it looks like, you know, we're going back and forth on the same ideas, although if you think about it like that, okay, it looks trivial, but actually it's something that it's not really like that, because in with the advent of software-defined networking, the possibilities, and in this case, the programmability that was introduced in the network was something that was unprecedented, something that was certainly not there before with the independent domains that were interconnected by IP gateways. So I wanted to present this example because I think it's sketchy, and also because I think that it's a way to show that it looks like we're going back and forth on the same thing, but actually we're gaining something at every step. Anyway, back to the main topic of software here. So yeah, in networks, the advent of software was really something that had a large impact. In fact, we might hear about the software revolution. So not just software evolution in communication networks, but also software revolution. This is a term that it's been coined probably 15 years ago now, but I like it very much. I decided to keep it. And it really concerns the fact that software and, well, I would say the phenomenon of network softwarization really is all about a transition, so a shift from networking infrastructure, which was mainly centered on hardware, so on devices that were good at doing something and optimized for that, to more software-driven architecture, in which we have general computing nodes that are able to be programmed and to perform different functionalities based on the software running on them, right? Of course, in very wide terms, of course, the role of software is more and more visible, like everywhere, even to I would say non-experts, like people that are not necessarily involved directly in the software aspects generally, because software is simply pervasive nowadays. In fact, starting from, well, even before 5G actually, but even more so starting from 5G and beyond, with service-based architectures, with the actual like explicit mention of software-defined networking and virtualization functions, so virtualized function within the 5G standard. The role of that has been so very much prevalent. The Internet of Things, which is a paradigm that it's widely acknowledged and widely discussed, which is really all about data, meaning that it's centered on handling, moving huge quantities of data, and needing to do that in an efficient way. And in that, software technologies really help and can really make things scalable and reconfigurable, which is something that is really important to that. Even other services that we always use, even without noticing, like content delivery networks, for example, are something that really benefit from dynamic deployment across the infrastructure, and dynamic deployment is enabled by a softwareized approach. Then everything about computing. So the way that we access services on the cloud, which then are deployed also on the edge, on the fog or the dew, and all the other computing paradigms that we use even seamlessly without knowing, are enabled by software. And of course, virtualization is all about using software to share hardware resources among different processes and different functionalities. So this is to give some kind of justification, some kind of motive why software is actually so relevant and should be regarded as such, in my opinion. Also, often the trend of softwarization is linked with programmability, which makes sense because really the two things are kind of intertwined. So they are different things, but they are very much close. They're intertwined in this sense. So yeah, this is what we observe, right? So in the modern telecommunication industry, we observe this kind of situation now. Well, I would like to try to describe how we got here, right? So how this whole network softwarization thing come along. So I like to think that it basically, came from learning. So learning from things that happen in another context or other scenario. For example, look at the computing industry, right? Typical example. I'm sure I'm talking to experts also in the field, so I'm repeating something that surely we have already, talked about multiple times. But I think that in this context, it's really interesting to see it this way. So in the computing industry, well, at the beginning, we had, again, very good, very specific hardware that was good at doing something. And then we got to general purpose servers and computers that could be, that you could just install an applications on top of it, and then have the computer do whatever function without changing the hardware. So the hardware was the same, and the application was really what defined the behavior of the device. Really, in networking, this is something that also happened with a couple decades of delay, but that happened. And again, we moved from a situation with which we have switches that were very good at forwarding packets to switches still, but that could be programmed, right? So devices that are good at forwarding packets, but that are instructed to do so by applications and by following some programmable logic. And this is basically what SDN, or software-defined networking, is all about. Well, regarding also the sister theme here, that is virtualization. Virtualization came along basically again by learning from what happened with cloud computing. Now, with cloud computing, services are virtualized and are offered as a service, so just without any additional worry for the user. They're virtualized and they're deployed somewhere, and the user just uses them. And learning from that, by applying basically the same approach of cloud computing to network functions, here we got network function virtualization. So an approach in which we can leverage virtualized instances of functions, in this case of network functionalities, that are run somewhere by someone, and we basically ask that someone to provide those functions to us. Again, in order to do so, there is some level of programming involved and need for programmable interfaces. So this is also why I'm saying that the theme of softwarization, the theme of programmability are strictly intertwined. Well, these two paradigms, SDN and NFV, are really the two things that enable a programmatic approach. So together, they enable the current way in which we perceive and work with the network infrastructure, really. In which we usually tend to assume that we can program the way that the network behaves. Okay. When I say now, I mean in the let's say the new millennium, the new millennium at least, the last 15 years. However, let's call it the road to network softwarization started way back. When I first read that, I was kind of surprising to me, because I was used to think that the road to network softwarization started I would say in the 2010s or in the 2000s anyway. So not so long ago, but actually we could trace the start, of the road to softwarization as far back as the 60s, in which the first concepts of digital network for digital networks came out. And if you think about it, well, digital networks kind of suggest the idea of having something which is at least compatible with software, with or something that can be programmed in a certain way. So it's easier to when you have the concept of digital network, it's easier to start to think about how to program them, especially, well, of course, in hindsight, it's easier because now we're used to that. But in the 60s, it was an innovative concept that was really the first concept on the way to softwarization. Then, of course, this evolved slowly, but just because of the requirement of the market and the limits of technology that you needed time. So although although this road started in the 60s, or we could trace it back to then, the real breakthrough really started happening in the 90s. So around 30 years ago now. In fact, it's in the 90s that we have the first concept, the first attempts, also practical attempts to actual network programmability. And in general, of the abstraction of functionalities from the network to some other entity, some other layer that can be programmed, that can be used to program the way the network behaves. Okay. So I would say the most exciting decades for network softwarization would be probably the 90s, between 1995 and 2015. I've called them here the two exciting decades, because I think the decades in which the real breakthrough really happened, starting from the concept of active networks starting from 1995, 1996. Active networks were basically an approach that envisioned providing programming interfaces or network APIs, basically to expose the resources that network nodes had, which is really the first concept of packet network programmability, in fact. And actually, I find it interesting that as always, this approach was kind of met with some hostility by the network community, because the internet community said that the internet was based on simplicity. You know, just every node knows how to reach the next one, and that's it. Okay, so I find it quite peculiar that this is a common theme. This is also kind of the same sentence that was said to Claude Shannon, and also to when the RSA protocol was introduced. So it's always like that. But yeah, in the 90s, we find the first concept of packet network programmability, and also of some kind of virtualized execution environments that allowed for the programmability of nodes. Then also the IETF, so the Internet Engineering Task Force, which was really becoming a thing, I would say. I mean, was really gaining traction at that time, also because the internet was fairly recent by that moment. The IETF proposed an approach for the separation of where we take decisions, the control plane, and where we implement decisions, so where we enforce those decisions, or the data plane. So probably the separation between these two concerns, so between the control plane and data plane, can be traced back to around the year 2000. And this IETF approach, called FORCES, which stands for Forwarding Control Element Separation, it's basically aimed at trying to standardize communication between the control plane and the data plane, allowing for some programmability. This approach here really is what the MPLS protocol is based upon, right? Or, well, protocols like MPLS, so label switched approaches in general, I would say. Now, these approaches are based on forces, and in particular on the path computation element approach, in which we have some element, in this case called the path computation element, which is not a data plane element. So it's not a router, it's not a switch, it's not something that forwards packets, it's something else that performs the traffic engineering, performs the optimization, performs the decisions on what should happen, and then exchanges messages with the network devices and instructs the network devices on how to behave. In this way, basically, really breaking in a good way the best next stop approach of IP, right? So now, for any reason, we can decide to steer the traffic in a way that is necessarily not the one that goes in the direction of the destination immediately, but even with different choices, which might be useful to implement traffic and routing policies, traffic engineering, and so on. And again, so yeah, at this point we are beginning of the new century, I would say the 2000s, and with the introduction of the separation between control plane and data plane, here comes OpenFlow, or I would say the protocol that it's usually mostly credited for separating control plane and data plane, although probably it's not necessarily the one that did it. Now, OpenFlow was thought to generalize the behavior of forwarding devices and make the whole thing programmable in a way that we basically instruct the devices on what to do based on some programming that happens in the control plane, so somewhere else that happens again in another element, the controller, and then the devices just applies it, right? OpenFlow and this approach generally also introduces the vision of a network operating system, so of a platform on which we can install applications and that will then guide the behavior of the network itself. Well, OpenFlow really also helped opening the box. Like, by opening the box, I mean separating the control and data plane functionalities also in the devices. In fact, recalling what I said before when we moved, when with the comparison with the computing industry. Again, here, before the separation of control plane and data plane, we had devices that were really good at forwarding traffic and decided how to forward traffic based on some protocols that allowed them to communicate with other ones, right? Then with OpenFlow and generally the SDN approach, we separate the two concerns, and we have some layer in which we decide what to do and some layer in which we do what has been decided. And the two layers communicate with an API, of course, through an API implemented by OpenFlow in this case, and really giving rise to SDN as we know it. So with the typical and very much widely discussed separation between control plane and data plane. Well, I think something smart about OpenFlow is that also it leverages technology which is there, to be honest, because as I said, we started from devices that were really good at forwarding traffic already, and then also took decisions. But now, so basically we just don't have them take decisions, and we still have them forwarding traffic, and they can do that very well. In fact, the all hardware acceleration that can be used for that is still accessible also to OpenFlow, but now the difference is that the logic, the control, is somewhere else, like in the controller, now separating the two planes. When I say that we can leverage technology that it's already there, it's because what I mean is that before programming the switches, really, we still had, again, tables that needed to be looked up, right? And the table previously being mainly composed of, just a destination. So like think about the IP routing table. The IP routing table has associates a certain next hop to every known destination. So it's really a way of checking what's the IP address, the destination IP address in the packet, and based on the table, decide where the packet needs to go. In SDN, in OpenFlow, with OpenFlow in this case, the concept is really the same, but extended much beyond the simple, just the IP address, but also extended to so many parameters, including the MAC address, including, well, the port, so including layer 2, 3, and 4 parameters, okay? The representation that we find here is for, it's not for the last version of OpenFlow, actually, which includes much more than that. And based on what's the line that best matches the packet, then the packet is forwarded, the packet is processed in some way. So an action is applied on it, right? So this match action strategy was not invented by OpenFlow, was extended or enhanced with OpenFlow, but it's something that has been around since, IP routing tables, if not before. So the benefit of OpenFlow is the capability of being able to program this, right? So to program the behavior of the network. Since I'm saying that, I would really like to specify also that one could be tempted in thinking that OpenFlow really makes switches programmable, but is it actually so? Not sure. Well, I mean, it can be argued that where the actual programming happens is not the switch. So with just talking about vanilla OpenFlow, so the switch is not really being programmed. So the switch has a table which has been filled with information that the switch is very good at accessing. It's very fast at accessing, but it's not really doing any computing. So it's not really, thinking about what it's doing, right? So it's just basically following a table. So the programming with OpenFlow happens at the control plane, not necessarily, not in the devices, which is not bad necessarily. I'm just saying that this does not make the switches programmable. This introduces programmability in the network, which is something different. Well, or enhances programmability in the network. In fact, everything should still happen through the controller. And the OpenFlow switch is just a simple forwarding device, which executes what has been decided in the controller. More on that later. I'm saying that this now because it's going to be also an important reference for in a short while. Also, clearly, by doing so, basically by having the switch needing to go through the controller, the performance in the data plane is very much affected, of course, because every time the switch doesn't know what to do, every time the switch doesn't know what to do, the switch needs to ask the controller, and this is not something that is always feasible. Let's hold this thought for a second. I would just like to finish the very nice timeline here, just by mentioning that parallel to the evolution in just pure networking, we cannot avoid also mentioning the evolution in virtualization. So the capability, the possibility to virtualize, so to share physical resources among different users, different processes, tenants, okay, which is made available by the use of software in, and particularly in this case, in the implementation of virtualized environments, or virtualized, well, just applied to network, even just virtualized LANs, like virtual circuits, VLANs, VPNs. This is something, again, that evolved and that really had the breakthrough in the same 2 decades, right? So between the 90s and the 2000s. So this timeline ends, well, because it was taken for a very nice survey, but it's a little bit aged. So this timeline ends at in 2015. But there's still 10 more years to account for, right? From 2015 to now. And of course, evolution did not stop. So of course, things have still happened, right, till then. So I'm going to try to add on this, starting to focus only on the networking aspects for the moment, and then we're going to extend. So maybe this is a biased opinion because I started studying these things in 2013, something like that. So to me, the years just before that were like the golden age of network softwarization, meaning the time in which breakthrough technologies came out and were those that were on which the rest of the technologies after, were based upon. Well, as I was saying just a couple of slides ago, yeah, so OpenFlow really, what OpenFlow does is to allow the separation between control plane and data plane in a more enhanced, in a more flexible way, really just relegating the programmability to the control plane. So we're not programming the switches, the programming happens in the control plane. However, OpenFlow also can suffer from performance problems, especially when, with high data rates applications. In fact, we cannot think that having that we can support a very high data rate application by needing to ask to the controller something, about every new flow that we don't know how to process. From the point of view of the devices, that wouldn't make much sense. It would introduce so much latency. And so for that, and here I would like to recall the original concept of going back and forth, but I'm going to clarify on that. So to tackle that, programmability was actually extended to the data plane with new technologies, new protocols like P4, for example, then DPDK, eBPF, and more, which really enabled the data plane to be programmed and to also support high-performance switching, high-performance processing in a programmable way that was not feasible before, and which also allows for the deployment of new applications like in-network telemetry or network computing. I would like to spend a couple of minutes on this, just because, again, I would like to clarify what I said before, which kind of sounds like an accusation, but it's not, because it's not like we are actually giving intelligence back to the switches. I mean, not necessarily. So again, going back to IP, so what IP used to do was basically forwarding based on decisions that were taken in a distributed way by devices that communicated with each other with protocols. So this was even quite efficient to some extent, but limited to what the protocols allowed. Okay, so also for this reason, we evolved towards in the direction of being able to program that. Okay, so And we, as I said before, we got to the situation in which we have switches which were already very good at forwarding, and so forwarding devices in general, which were very good at forwarding. We basically removed the decision capabilities from them, and we gave the decision capability to some control plane, and still keeping the forwarding there. Now, realizing that this might not be necessarily the best thing for high performance applications, with data plane programmability, we're kind of giving some intelligence back to the switches, but we're not at all going back to the point in which we were before. I would like to stress that, because it's something that I've been scratching my head about for some time. Because really, what we're giving back to the switches is just a part of the intelligence. It's just the capability. It's basically an offloading of some of the functionalities that make the switches able to cope with high performance applications. But we're still programming them from a control plane, and we are just offloading some programmable functionalities to a data plane, just to make sure that they can keep up really with high data rate applications. So yeah, just wanted to share these thoughts, because I think they're really I think it's important to consider that. Well, going back to actually going on with solutions for programming the network, programming the data plane, I would like to briefly mention some hardware-based data plane programmability solutions. The first of which being OpenState. Really, OpenState is a way to enrich what the OpenFlow switches can do. So the match action, approach of OpenFlow switches, with also some stateful packet processing. So with OpenState, really, we are enabling the OpenFlow switches to go beyond a simple table. So not necessarily just one table that you look up and whatever the table says the switch should do. But with OpenState, we are really including some stateful capability, so that the switch can be programmed as if it is a finite state machine. So we can have multiple stages in which the switch can use to process the traffic, which enables applications that require memory, right? The example in the figure here, it's a port knocking sequence in which we want the switch to let through only the traffic that knocks, that really sends a packet on a specific sequence of ports. And to do that, there's no escaping the fact that we need memory, and OpenState really allows to do that. So this is one approach to actually program the switches, in this case based on a finite state machine. Another one, and probably even more widespread, would be a new actually, this other approach comes from the realization that probably we need to also modify. We need to move on from the simple, forwarding device that has one or more tables and that just follows the tables and processes the traffic accordingly. But we could move towards some forwarding devices that have some, processing capability in them. And this is what the PISA architecture, or protocol independent switch architecture, it's mainly about. Very briefly, what the PISA architecture allows for is basically to reconfigure multi-stage match action pipeline, having some logic unit that can be configured in a way that we implement some, actual logic, in the sense of some programming in the switching devices. I'm immediately moving to the most widely, known application of that, which would be P4. Now, P4 is a language that allows for to program this kind of these switches with this architecture. And again, in very just divulgative, very large terms, very wide terms, I just want to introduce P4 as the language that allows to have basically to program the behavior of these switches of forwarding devices with intelligence in them, by enabling them to handle any particular, any specific and new protocol. So it's completely protocol independent, of course, and even something that is just specific to the application that it's being run, and really introduce, this really introduces a very high level of flexibility and reconfigurability that was not possible with previous architecture, of course. Before is domain specific, as in it works on devices which are done in this way, of course, but it's also really, really, really powerful, and it's really a solution that, of course, it's rightfully so, really, really widespread. Well, in addition to that, we could also leverage some programming capabilities in network interface cards, because for up to now, I've only talked about switches, but why not considering also network cards? Because if you think about it, network cards are, I mean, the point where all the traffic goes through, from each computing node. So why not also introducing some programmability in them? And this is the concept of smart network interface cards, or smart NICs, in which the idea is basically to add programmable hardware like FPGA in network interface cards, so that we can further offload functionalities to the data plane in this case. Again, in the direction of trying to enhance performance and cut and cope with the needs of very high performance services. Having all of that, once all of that is established, there are new applications that really open up. I've already mentioned this few, which, for example, are in-band network telemetry, or INT, and in-network computing, which really leverage the capability of processing that is available in the network devices, well, to support advanced monitoring. So to make monitoring of devices and monitoring of the traffic that really flows between them more efficient, and reduce latency, of course, which is also always very important. And also, within network computing, we are offloading some computation to the devices themselves, right? Possibly offloading to them some part of the application processing, so as to offload, to remove this burden from the computing nodes. This is a way also to show that computing and networking are not really separable, right? So computing and networking in the age of software really go hand in hand. In fact, this is also the main point I wanted to make in the next few slides. Virtualization is basically the counterpart to network softwarization, but in the computing world. So for that, here I'm showing a separate timeline, although it's not going to be separate for long. But in the same logic of trying to give a historical perspective, I would like to start from from way back in time, starting from the 60s. Again, apparently a very prolific time for software technologies, or what was going to become software technologies in the 60s, where IBM basically started introducing some implementations of what could be called virtual machines. For example, the M44, which is a system that allows for the sharing of resources in a, well, what we would call now a virtualized way, right? And same for containers that, well, actually came out much later than that. In fact, containers were an idea that started with FreeBSD in around 2000. But still, I would say that these two things were definitely the first pioneering approaches to what now we call virtual environments, right? Well, I assume that similarly to the networking industry, also in this case, things really didn't, started take off until recently, because of the lack of, a need for that, which then become very much evident in starting from the 90s, where also, you know, some applications also came out for virtualization that really launched this approach. In fact, I would say that one of the probably most important applications of virtualization would be cloud, the cloud. So cloud computing, so the cloud computing paradigm, well, contrarily to, so as opposed to other paradigms that are really somewhat like vague and not very much well-defined, actually has a definition. So in fact, again, as a time period, we're talking about the early 2000s, the 2000, yeah. And a definition for cloud actually was given by NIST and NIST. And well, cloud would be basically a model for to enable you know, a way for users to just ask for a service, just ask for something, for some functionality, and just pay for that and have it in a way that it's well, that really relieves the user completely of, you know, any worry about how the functionality is to be deployed, how is deployed, how, you know, on what server does it live on, and any physical aspect of that. And really launching the idea of utility computing, really. This concept of having functionalities that are offered in a ubiquitous, convenient, and on-demand way, it's really something that it's central to how services are offered in the network nowadays as well. So cloud becomes really kind of the centerpiece of a very much larger shift that then happens in the next decades, up to now. That it's really about services and how to offer them. In fact, there are several ways to offer services, and cloud has several examples of that. I'm showing here just a few of them, which are the most famous ones, but I really have seen everything as a service in the past. We all have seen really everything as a service in the past few years. Just to reference some of the most you know, widespread ones, the cloud approach really introduced, you know, the idea of software as a service. So we have we just want to access an application that it's running somewhere, and we just access and use it, like Google Drive, for example, or platform as a service, on which, well, sorry, I should have said Google Docs mostly. Then platform as a service, in which we want to access some environment in which we can program, maybe, in which we have libraries, but no application running. We want to implement our application and run it. Or infrastructure as a service, in which we just want to access a server somewhere or a virtual machine running somewhere, in which we can install applications and programs and work on that. And these are like the three most famous ones. But another very famous one would be functional as a service, which is like a more lightweight version of software as a service, if you will. But the list goes on and on. There are so many more, and there are the possibilities are really even growing, you know, in over time. The number of these possibilities increasing over time. So yeah, cloud really became kind of the centerpiece of a sub-revolution in the whole software revolution, I would say. And of course, new platforms were needed to be created and needed to be deployed for the management of these functions, right? Of these cloud functions, including, for example, OpenStack, which is a platform for managing virtual machines that came out in 2010, Docker and Kubernetes, which are platforms for running and managing containers. Now, I have distinguished virtual machines and containers, and since the nature of this tutorial is supposed to be, you know, for also kind of introductory, I would like to spend a few words on the difference between them, although I know it might be basic. But I think it's important to this talk. So in virtualization, there are several ways in which we can actually separate, you know, physical resources into virtual appliances and virtual resources. And one of them would be with virtual machines. Like virtual machines, as we know, are a way to virtualize the whole operating system. So basically to have a guest operating system running on top of a host operating system, really. On top of which we can run any new functionality that is supported by the guest operating system. And in the following, I will refer to virtual machine-based functions as VNFs, so virtual network functions. But a more lightweight version of that would be containerized network functions. So basically, using container technology to still obtain network functionalities. And containers are a more lightweight form of virtualization that really is based on layers. So it doesn't really virtualize the operating system. It really uses a container engine like Docker that interacts with the operating system and that allows for the execution of functionalities. As I said, in a layered way, meaning that only include the layers that are required. So, for example, a container might include additional software like binaries and libraries that are used for a certain functionality. If those differ from the ones of the host operating system, or if for any reason we want to separate them. But a container might even be as simple as just a program, like literally a software that runs on top of the binaries and libraries offered by the host operating system through the container engine. And the container in a very light way just offers the software, right? The program on top of it. Now, this opens obviously to a really large degree of, a really large amount of possibilities on how to deploy functions in the network. And actually, this is so, I would say it's so convenient that we should also think about ways on how to cope with, the expected workload, because of course the workload with in services that need to be deployed in the network can increase very quickly, actually. And so we need to think how to cope with that. So how do we, what do we do when the functions the virtual function that we have deployed are not enough, so are no longer enough? And for that, we can think about scaling. Now, the typical approaches to scaling would be scaling up, which really means adding more resources to functions that we already deployed, or scaling out, which means adding more replicas of the functions that we have deployed. Which is good, which really helps coping with increasing workloads. However, there's a limit, of course. And the limit comes from the fact that network functions and application functions are not really the same thing necessarily, meaning that depending on what our virtual function does, just increasing its resources or increasing the number of functions that we deployed might not be enough to cope with the traffic that those functions are subject to. When I say that network function and application functions are different, what I mean is that really, network functions are something like traffic shapers or firewalls or load balancers, so things that operate at the network level. So in the kernel, right? Whereas application functions would be something like authentication functions or content delivery or database queries or things that operate in the user space, right? And this difference really plays a huge role. In fact, there's a bottleneck in that virtualization really highlights. There's a bottleneck caused by the interaction between the user space and the kernel space. In fact, every time we need to basically just to give traffic to a virtual function that is deployed, or a containerized function, whatever, that it's deployed in the user space, we need to copy those packets really from kernel space to user space. And this is something that might not be fast enough for some applications. For this reason, technology has evolved in a direction of new ways of programming the network, programming the data plane in this case, now with software-based solutions. What I discussed a few minutes ago was hardware-based, so like the peace architecture, so with P4, and those solutions were mainly hardware-based. Now, we also, over time, got solutions that were based in software. So software-based solutions for the programmability of the data plane. For example, DPDK and DBPF, which are the two most famous examples, that in different ways aim at making the processing of data more efficient and faster, of course. In the case of, well, DPDK and related technologies, basically by just bypassing the kernel, really. Whereas with eBPF, the idea is to put the network functions in kernel space. So just running the network functions in the kernel and no longer in the user space. Both these things, in different ways, try to make, you know, the processing faster, really, and also enable, you know, again, as usual, the usual objective, so faster processing. Well, with this plethora of technologies, of course, also come, you know, the need to have platforms that manage them, of course, and paradigms that describe and manage them. And at this point, I think it's clear enough that it's impossible to distinguish. I mean, it's impossible to keep computing and networking, the computer networking evolution separated, because most of the things that, you know, I just talked about are really about the interaction between, you know, some networking functionalities, some computing functionalities, of course. And for that reason, over time, paradigms like NFV, for example, came out, and multi-access edge computing as well. And then platforms for orchestration, like OSM, for example, open source Mano, and so on. So many platforms and solutions came out, and really the line between networking and computing is really blurred. And I would say not only the line between networking and computing, but also the line between network segments. Because at this point, where is the function, really? Are we deploying that should we deploy a network function in a data center? To deploy it at the edge? Like, do we have like networking capabilities at the edge and computing capabilities at the edge that we want to leverage in order to have, you know, the service? So it's really something that should be, of course, taken into account. Also, we should also take into account that this is not stopping here. So the timeline here ends a few years back now, like, but starting from 5G, like even more with 5G, but even from before. And even more so with 6G and beyond, to whatever G we're going to reach, this is going to continue. So we're going to have, you know, the need for some holistic way of operating that. And so the question is, okay, now how do we manage all these elements, and how do we consider that we have user and services to satisfy, really, and we have so many possibilities on which to deploy services, to deploy functions, and so many resources? Well, you know, kind of simplified response to that would be with network orchestration. So network orchestration would be the new way of you know, automate networking. So the new frontier of network automation. Roll the credits. And in network orchestration, really, what we are trying to do is to, again, learning from something, so in this case, the cloud, and trying to go beyond just simple automation, which is basically, you know, coordinate what happens in the network domain. But we need also to, well, decide how to use our resources, decide how to distribute the workload between the allocated resources, and how to deliver the service to the user, right? So it's really a wide field, of course, with also wide challenges and requirements. In fact, in network orchestration, we should, you know, coordination would be also one of the main points. So one of the main challenges. So we should coordinate everything that's happening, and also including also the service provisioning to the user. And and trying to do so in a way that is as general as possible. I'm making here just, I'm putting here the word end-to-end with a question mark because I'm going to come back to it in a second. Also, I'm going to go slightly over the original hour, which is expired just now, but I only have a few slides left. Okay, what I think is really important to specify, to to denote about network orchestration is that with network orchestration we are applying yet again a decoupling. So we are separating the some kind of resource layer, that it's what we've been talking about up to now, from a service layer, which is something that is mainly concerned with provisioning services to users based on service level agreements, and is not concerned with technologies, really. And probably this separation is necessary for the same reason that the separation between data plane and control plane in software-defined networks was beneficial. So by doing so, the concerns of service providers and of resource providers can be separated and can be tackled as separate problems with well-defined interfaces in between. Talking about interfaces, actually, the standardization, so many standardization bodies, including ETSI, have been, of course, tackling about this. I've been talking about this, of course. For example, well, NFV Mano now, it's kind of dated at the moment, but really highlights the need for a structured approach and for well-defined interfaces between functional elements that enable service provisioning, which in turn enable, well, a programmatic approach to service provisioning. So OSM, or open source Mano, would be basically an orchestration platform that allows for a very high-level description of what the service should look like, and then the platform takes care of installing the, creating the virtual machines, creating the connections between them, and making sure that the service, as it's defined as a service, not as a collection of resources, just as a service, is provided to the user. Similarly, but with containerized network functions, Kubernetes tries to do the same. So Kubernetes will be, again, a kind of orchestration platform for containers, which again supports very high-level description of the services that need to be applied, need to be created, and provide them to the user. ETSI has also been working in the direction of trying to understand how should we, make it zero touch. So how should we automate the whole thing, so the whole orchestration thing, like end-to-end and across multiple domains. In fact, I find really interesting this cross-domain interface integration fabric that I'm pointing out with the error there, that comes from the ETSI Zero Touch Service Management white paper. Because when you have such a wide scenario as the one that I've shown before, you have also, the need to make sure that everything can kind of works together. An approach to that would be, this cross-domain integration fabric would be an idea for that, which in practice is not so easy to implement because it requires the coordination between multiple domains. In fact, orchestrating resources across multiple domains is something that is being tackled in the literature in the past years, of course, but still requires a lot of investigation, I think. And well, in this case, the case that I'm showing here, it's a paper from a European project from a couple of years ago that suggests to have independent domain orchestrators. So each network segment has its own orchestrator, and then all the orchestrators are kind of orchestrated by another one, which is an approach. Or this could be done with a kind of marketplace approach in which we have resources available and then orchestrators basically bid for them and obtain them. And orchestrators in the separate domains have resources and bid for services so that they are assigned the services that can handle. It's another interesting approach. But what I would like to point out is that these things really go in the direction of end-to-end. But do we actually need end-to-end? And this is my point that I've been trying to discuss for some time, and still I think requires a lot of discussion. Because what we really need probably is edge to cloud. So the end-to-end services are really few. the end, like maybe phone calls are actually end-to-end to some extent, if they are so, because a phone call really is from between a user and a server somewhere, which then processes the audio and gives it to another user. So really, it's basically two edge to cloud services again. So two, I would say, end user, so end to cloud service, if you want. So this is just some food for thought again, due to or possible point of discussion. Because probably end-to-end is not necessarily the thing that should be investigated. Well, in the same kind of provocative manner, I would also like to end with this other idea for a morphable approach to networks that really tries to answer the question: what would happen if we could think of being able to program single layers in the stack, like, okay, in the network protocol stack? Well, the question arises from the fact that usually services in network deployed as a concatenation of application services, really, or, well, generally there's some kind of correspondence between each layer, right? Horizontally, or services are deployed as a collection of vertical integrated functionalities, including, for example, application to networking functionalities, like containerized somewhere, okay? But what if we could mix them up? So what if we could think of being able to program the functionalities of the single layers and combine them? This requires probably some programmability in the data plane, surely some programmability in the control plane, and surely some orchestration. So this also again calls for additional layers of orchestration in that. Okay, so to conclude and to launch the second part of the tutorial, I would like to conclude by again stressing out that the whole keyword for all that will be complexity. So there are things to be handled, of course, as in every engineering aspect, I would say, and there are challenges that network softwarization helps in handling, but also challenges that network softwarization kind of introduces, of course. Because complexity is really everywhere. The devil is in the details, as I really much like to say, and it's I think that the research needs discussion. So we need more research both in terms of new technologies that can enhance the current ones, and in terms of architectures. I think that also the architectural viewpoints will be really important, and all of that doesn't even consider security, which is something very much important, as well as AI, so artificial intelligence and machine learning, which have the potential to kind of revolutionize all of that. In the direction of going towards more simplicity, so less complexity, the next part of the tutorial is going to talk about SDN controllers with a microservice-based approach. I will leave that to Domenico next session. So with that, I would like to conclude, and thank you very much for the patience up to this point.